happened and hopefully will keep on happening. I prefer to stand when I present because otherwise I fall asleep myself. So yeah, this presentation will mainly be based on what I did during my PhD, which I defended at the end of last year. And here I'm going to focus on a specific part which might be the most relevant to the discussion at hand in these 2 days, which is about the operationalization of visual similarity. How can you leverage a almost formal representation of organization of visual information to help research track patterns in large collection of images? So I start with a couple of examples. So this one that probably everybody knows by now, of the Sleeping Venus by Giorgione, and how it has impacted and influenced a lot of following representations, so the Titian one, of course, and then a couple of centuries after the Olympiad by Edouard Manet. But rather than just a couple of examples, the space of this this representation and how it was influenced, I would say it's not just direct connection. There are not categories. It's a continuum space, as we heard before already this morning. There's a form of continuity, and here it's semi-organized by visual similarity and also kind of by the way they happen and how it spread it from a center. And of course, it's just a selected, completely arbitrary set of examples. There are many more than this one, but that's the kind of things we were interested in finding. Assuming we have a large collection, can we find more of this? Can we put them more into context? Another example of what kind of patterns we were interested in, why this project got started, was if you take different, I hope you see them a bit, especially in the back, given they are not very high contrast. So like 5 different images by the Bassano family, but if you look at each of them, there are kind of the reiteration of same patterns that were used almost as copy-paste in this kind of workshop practices in this way. And this kind of patterns recurrences and visual correlation that's kind of independent of form, of content, because there are 5 completely different representations, is also something that we're interested in. And maybe a last example to bring my point forward is the gesture and how it's independent of the subject at hand. So here, Mary Magdalene, here's this Lucretia, that's Eve, and no, that's Cleopatra, sorry, Mary Magdalene is here. And here you have some letters, that's Venus, and there's kind of almost transition of forms and how people have kind of converged on some specific posture, maybe more aesthetically pleasing, and did they all converge separately or not? So that was the original motivation of the project, explore the propagation of form, as this reference of motifs are the proof of very complex relationship, either workshop practices, almost homage, as Haro was say, pastiche, parody, or any kind of correlation that can happen. But because of the scale and the amount of data, it's a difficult task. And also, mainly important is like you're only as good as the quantity and the quality of data you have and how much you index in order to find this kind of interesting elements and interesting correlation. So the original idea was to say, well, there are photo archives, and in these photo archives, there's a lot of information necessary. It's just like a lot of it was not digitized. Now it's getting better, but a lot of it was not digitized and not accessible. So in order to search through it, you might have as best a very simple metadata search system that allows you to find the element you care about. But everything was here. So the replica project was said, well, it's already grouped in the photo archive. So step 1, digitize. Step 2, something. And step 3, well, enjoy it and do something with it. So I'm not going to take credit for this idea, of course, because that's what the original project started by Frédéric and Isabella, who were both my supervisor during my thesis. But then I was responsible for a lot of the execution after, like, to fill in the gaps. And the case study we worked with was, we had a close collaboration, we still have actually, with the Giorgio Cini Foundation in Venice, that was under the umbrella of the Venice Time Machine that the TH Lab is very famous for now. but they have a very large collection of images, 1 million images, 1 million photographs that they have, and it's kind of huge shelves next to each other with a lot of documents in it. And there is some form of index that they had. But what was interesting, it's large, it's very, what would you say, consistent, coherent, because it's very focused on Italian art and Venetian art. And it's very extensive on that specific topic, so it's a very way of trying to see if this kind of approach were going to work. So if you take the global outliers, well, we have this stack of documents somewhere, and hopefully you wanted to make them navigable, searchable, and useful. And how can we find something? So of course, if you fill in the gap, there were quite a few steps. And the one that we care about the most today, I think, is kind of this organization of the visual information. How can it be kind of operationalized? How can you learn from it and try to have this back and forth interaction between the need of the user and the research question and the digital model and the visual model, the computational model that we use behind. I will still quickly talk about these two parts. So we still follow through kind of pipeline, but spend probably more time on the meat of the content. So the first part was to say, okay, we have this stack of documents, but we want to extract them and organize information there. So if you've been to a photo archive, it's very common that there are this large cardboard with a glued black and white photograph under it with some form of metadata at the top. So first we had a collaboration with the Factum Art Foundation in Madrid to create a very efficient scanner to digitize this document. That's sometimes recto-verso document. You might have like handwritten information in the back and so on and so forth. And they created this wonderful rotating table that someone put the document here, it gets scanned on both sides, and then someone take it out. And they could scan like one document every 4 seconds. And so you get a lot of scans coming to us. And the kind of document you get this very generic form of document, but that's not very practical for using them and analyzing them directly. So there's a whole process that was not part of the original project that was to really look at the images and photographs directly, but there's this whole set on both ends that, well, in order to get the data, you have all this work, but if you don't do it, you don't have data and your project does not exist. And on the other hand, if you have if you have a very good algorithm, a very good data, but there is nothing to show and for people to use it, it's useless as well. So you have to fill in all the gap for the small part in the middle to be useful. So for this, you can use also convolutional neural networks that usually can be used for classification, but you can use them for document analysis very well as well. We've had very good success in order to extract all the different parts we're interested in. Here it's some form of semantic segmentation, so you give some pairs of a scanned document with the different areas that you want to be separated, and then automatically, even if you have different layouts and different organization, you can separate, okay, here's the main document, here's the photographs I care about, and you extract all of this. But also, like, just as a side note, small parenthesis, this kind of approach can also be used for more generic tasks for document analysis in the humanities, for handwritten recognition, illustration extraction for history of the books, or just extracting documents from the scan, which is general. So you take your physical document, you get the scan, you extract the image, and you can also do OCR on all the parts of the chart and extract the different layouts, and then you can say, okay, this is attribution, this is a place, this is a... So you still have some form of extracted metadata and structured metadata for the whole collection, semi-automatically. After you can go even further. For instance, we took like all the detected attribution and try to link them with a knowledge database to know, well, if it's Tiziano, let's say, like which one is it? Is it like the main one or the second one? Is it David Teniers or multiple of them? So what are the standardization in the collection they use? So you can try to generalize this kind of idea of dealing with disobligation, collection specifics, compositional grammar, typos, and all of this. So I'm not going to go into detail, but you can do semi-supervised approach for this extraction. So in the end, if you do all of that, so there's 13 months of digitization, 13 months you can digitize 330,000 images, which is 50 terabytes of data that came to us, a bit of a pain to process. And all the images were extracted, which gives more than 2 million metadata entries with 95% accuracy. So it's not perfect, but very good enough that it's useful and you can already do analysis on it and work with it. And almost 3/4 of the attribution were correctly passed. So the main point here I just wanted to get across was this process that we did for the Cheney Foundation can be applied to a lot of the photo archives in the world. So technically, there's kind of unlocking of this huge amount of data that can be done. So now if we consider the most important part, I may slow down a bit here. So suppose you have 1 million photographs, or 2 million, 10 million, suppose. And then we saw here that there were 2 different tasks we were mainly interested in. So first one, we takes a different photographs of the same artwork. Because for a given artwork, especially the most famous one, you might have like 100, 200 photographs of it. And if you just use the data as a raw version, that kind of unbalances any analysis you do. And if you want to show results, it's cluttered with all this similar, like if you have the Mona Lisa, you have 200 of them. And these are things you kind of want to clean automatically, because otherwise it changes completely the view you have of your data. Kind of create statistical imbalances and so on and so forth. And the second one was to organize images based on the occurrence of patterns. So if you kind of try to formalize these 2 tasks, are fundamentally quite different, and we'll see why for multiple reasons. So the first one is more like almost a binary prediction. You have 2 photographs, and can I predict these 2 photographs are representing the same artifact, the same visual painting, the same paintings, the same drawings, the same engravings, and so on and so forth. And the second one is more looking to learn a form of a similarity function between images in this manifold of acquired photographs. So now that's where it becomes even more important. So how can we try to have a middle layer, a representation of the interaction between these images that both we as humans can interact with, that we can edit, visualize, and that computer can learn from and interact with at the same time. And finding this medium layer is usually the hardest part. It's finding an ontology that's operationalizable enough for algorithm and computer to work with, but useful enough for us to be able to ask our questions. And something that came quite naturally for us in a way was to say, well, we're going to use some form of graph. So we consider each photograph, each image to be a node, an independent element, and the only thing we will represent are connections between these nodes, links. And we can see here in this formalism that we use 2 types of different connections between the images. And so I'll go over them. So the first one is what I call physical connection. And this is relatively simple to explain. It's like you take 2 images and you take a physical connection if they actually have an overlap of the same physical object. So that's quite simple. But for instance, you see, like if you have 2 photographs which have a zoom of different parts, then A and B are not connected, for instance. Even if fundamentally there are two photos of the same physical object. But because there is no overlap, this is not something you can operationalize. There is no algorithm that looks at these 2 images and say, oh, it's are coming from the same thing. That's not a problem, because in your representation, anyway, things are connected maybe at the second order. So it's not like you're losing information, and it's still completely self-contained in the visual information. But naturally, that's not often the kind of representation you will go for, because you say, well, there are still like details of the same painting, so there is a connection with them directly. Well, from a purely visual point of view, not directly. It's kind of only the second order through the rest of the manifold, so of the visual manifold that you have. The other type of connections that we use in this formalization are what I call visual connection. And first, we have to think a bit about more about, well, what kind of visual similarity to occur, and how can we encode a type of similarity with a graph. And here we're a bit on a specific case, because we consider only one type of visual similarity, which is form and physical shape correlation. And we don't consider anything about color, we don't consider anything about style, whatever it is. So we only have one type of visual similarity. So we're not multimodal, unfortunately, it's a huge limitation of the current approach, but for the type of question we had, that was enough. And so how can you encode a type of similarity within the graph? So if we look at this example a bit more, the 5 different paintings, I see 2 that are very, very close variation from each other, from two followers of Leonardo, I think. 2 that are, you know, relatively close together, maybe not as much as these 2, but there's a significant visual correlation in the ways the composition is created. But if you look, for instance, at this one, which kind of correlate with this one in terms of like how Madonna is represented with her hand in the organization, but that this baby is much more exposed in its interaction with the Virgin Mary than the other one. So if you were to connect this, you say, well, maybe I connect these 2 because they're very similar, I connect these 2, but like this one, should I connect it with this one, should I connect it with this one? Is that relationship stronger than this one? It's kind of a hard, like, you cannot answer all the questions, basically. You have to assume that you have information about the degree of visual similarity. You might say, this is a stronger relationship than this one. This is a stronger relationship than this one. This, I cannot say. This, I can say. So the only thing, if you look very at the low level, fine-grained version, is the only thing you can say is you can only compare the relatedness of pairs of images. That's kind of the lowest level. And so you only have relative information and incomplete information. So from a mathematical point of view, you have a strict partial ordering of relationship strength, if you want to use very precise mathematical notations. So the only thing you can do are some form of this statement. The relationship between A and B is stronger than the relationship between A and C. There are plenty of situations where you cannot conclude. And that's already by using a very strict version of similarity. But so, if you consider that implicitly there is some form, there are some statements that most people will agree on if we describe precisely the type of similarity we get. So assuming that there's still there are still some information there that most people will agree on. It's kind of this Descartes approach. I will adopt everything, but at the end there are still things that people will find valid. So how do you encode that? The concept that I introduced, which was the visual consistency. That you try to keep a graph structure so that if two elements are connected, that means there is no element closer to them which is not connected. So for instance, here it's valid. Like if you look just only in the point A, that's valid because A and B is connected, but all the other are further than them. This is still valid, this is still valid, this is still valid, this is not valid anymore. Because here you've connected B with A, but C is not connected with A. So here you've kind of broken the stability of your representation. But what's interesting here is like there is no just one valid representation. The empty graph is valid, so empty graph has no problem because it cannot contradict itself. And the full graph is valid as well. But the thing is, iteratively, you can keep building it. So that's very practical for us, because from a data representation point of view, the only thing we try is like our internal representation, our database system, is to keep our graph, which we call a morphograph, but it's more like a space of morphograph, and we only want that graph to stay in the space of valid graphs. So people can modify, people can add data, they can change things, but we have to stay in that space. We can add more and more. But we can start with an empty graph, and eventually by people who's interacting with them, they add more and more information to it. And you have interesting mathematical properties that satisfy my little mathematician heart, but I won't go into it. So for instance, if you go back to this situation, that's valid, that's still valid, and that's still valid as well. And there's not one that's better than the other, they're all perfectly consistent. But they allow us to encode information about the type of similarity we want, and still being a representation that we can work with and enjoy and visualize and send to friends or whatever.
And sorry, the similarity here, is it measured? Is it represented as a number?
No, here right now. Here's like a way to it's
logical.
Here it's how we modify it. That's like the user, how we can modify it to represent this. But then we come how we can use that graph to emulate a function that will measure visual similarity, but try to keep these properties. Anyway. So I'll come to that a bit later. So, so if you look at if you look at a bit more, so you have physical connection in gray and the visual connection in blue here, so that the way we were interacting with the data and modifying it. So here it's kind of a very simple group of like 4 series and 2 photographs, which are actually the same one as this one. So you can organize your manifold of images with that. Here also, there is no information about time, so no information about metadata. We just like purely manifold of images. We're very honest about that. And sometimes you have much more complicated relation where there are like patterns propagation and how it's reused and sub-element propagated. It's a bit of an extreme case, but it doesn't happen so often. Another huge limitation here is that implicitly we're doing a bit of an assumption of complete knowledge of the database. Because if you connect something, if you connect 2 elements together as a user, you're implicitly saying there is no other image in this whole database that's closer to them, in a way. So that's as implicitly saying, I have seen the whole database of images and I'm saying this to you. And you cannot have that, technically, of course. That's a huge limitation of how you do it. But you can emulate that, assuming you have a perfect search system. You can try to emulate this complete knowledge of the database. But that's why it's a bit of an iterative process. Because you start with an empty graph and a basic search system. And the basic search system might help you to organize a visual graph. But the better the visual graph is, the more connection you have, the better you can train a search system. And then you can improve the kind of relevancies that it can give to the user. And then continually you improve and maybe correct, because you try to keep the graph as consistent and valid as possible and correct as possible. But I'm not sure it will happen 100% of the time. Probably not, but that's fine. You just try it as best as you can. But because you create this loop of self-reinforcement, the better the system is, the more things you find, and the more things you find, the better the system gets, and so on and so forth. So that's for like the formalization, which I think the most important. And not that you formalize thing is just engineering work. I mean, that's 99% of the work, but it's just engineering. So in terms of the first task, we want to have like a binary prediction system that take 2 images and directly detect like are they the same photograph, because that's a lot of work. There are so many of them, you cannot do that manually. And the other thing is, given the visual links you have, can you emulate an underlying simulated function that will keep these properties, and that way you can learn a visual simulated function that depends to how you encoded it in this visual graph. And I mean, here we use shape, but technically you could use another form of visual simulated that you care about to learn a different function, as long as you stay consistent with it. So when it comes to detecting physical connection, that's actually very important, because as I said, there are so many photographs of the same thing that it can clutter the database very quickly. And also assume that you digitize the Getty, you digitize the Hague, you digitize the Cheney, you make even more variations between them, and sometimes with different metadata, and it's almost impossible just from the metadata to reconcile them automatically. But visually you can, actually much better than you would think. And also that allows you to transfer metadata. Sometimes you have photographs. I think it was at the Frakes that had a bunch of photographs from Italian paintings, and they had no clue what they were. But if you take the photograph, you find the matching pair in maybe more documented database, you can transfer the metadata automatically. And it's quite interesting because here we're not dealing about visual similarity, but like unicity and uniqueness and like identity almost of it. So for instance, if you have a zoom here that's still the same artwork, because there's an overlap here, and if there is a restoration process, there's still like a significant physical overlap between them. But when there is a workshop series, they are very close to each other, but here you want to say, no, these are 2 different physical objects in the world. I want to know about that. I don't want them to cluster together because I'm losing information about the production of the production of humankind. And sometimes you even have weird cases of what is unicity. So that's something that happened in the Cheney collection. So that's a close-up of the Spring of Botticelli. But then you have other photographs, which are photographs in the Cheney collection. But they are basically Photoshop version, but like early 20th century manual Photoshop of this one to sell photos that that's actually better for printing or for whatever situation, it sounds better. But then, and depending on the level of perfectionism of the people, they kind of recreated the background differently because you had to fill in all the gaps. Actually, if you zoom in, you probably, some version we can still have like a shadow of the hand here, or like how well redone was it. But then, from an ontological point of view, is it different artworks, similar artworks? Because there is a whole creative process here. And it's something that happened generally also in this project, is that you start with something that you think are very clear categories in this situation. Oh, that's very clear. But there's always something that doesn't quite fall in either categories. And looking at the borders, when you do any kind of classification, looking at the decision border, and what doesn't quite fit in, usually brings interesting discovery and interesting reflections. But also, that's something we are terrible as humans to do as humans. So these are two different paintings actually, by Guido Leni. So I have these two, and now I have photographs. I have to know which one is it. So if you manage to find the right, or you're really good. I'm really terrible at this kind of. It's kind of playing several differences at the back of a surreal box, if you've never done that. But the thing is, you can overlay them and make this kind of visualization to highlight the differences. So I've come to, well, sometimes, it's more interesting to visualize the differences than visualize what's similar. And here, if you overlay them, it's just like a standard change of color. And here, you actually see the tiny differences that there are between the two versions. Which, first, is really interesting when you compare things which are extremely close. And also, it can highlight some kind of interesting situation, because that's a restoration process that was done. It looks more like a slim, fast advertisement, actually. But at some point, it was changed to fit a different kind of visual aesthetics. So like, oh, it's too slim, put some meat on him. And so now it's also quite interesting how close this workshop variation are. So these are actually transition between two paintings by a Greco. But despite the kind of very evanescent style that these two paintings were so precisely done that you can overlay them as like almost no single difference in the main line. You cannot see the difference between like the draping, which is slightly different, and so on and so on and so forth. So sometimes you start with a question, and by looking closely at it, there are other completely irrelevant things that pop out. So anyway, you can predict that very, very well with machine learning and computer vision. I won't go into detail, but the algorithm is much better than I am actually at predicting this kind of thing. Without this precise visualization, I'm totally unable to. But you can extract like all the physical connection that way. What's interesting is that allowed us to find so many metadata conflicts and so many metadata issues in the whole collection of the gene. And so you have these three different art pieces, and none of the metadata match. Like the attribution don't match, title don't match, the location don't match, but they're actually the same physical artworks. Probably with photographs taken at different point of their history, so we can move from it. And we actually found that there is basically almost 6% of the artwork in the gene which have more than one conflicting attribution, which was quite interesting to see, because we could come to them as like, well, you have 1,200 different artworks, not photographs, artworks, with more than one attribution in your own database, and I had no idea. And sometimes they are very striking. And here's something that's supposed to be the school of Raphael in a completely different place, and even physically everything is the same size. So it asks the question about the reproduction practices. Right. So come back now to the similarity learning. So we want to emulate the ordering information. So we have this graph of visual connections. And from that, can we learn a similarity function? Can we learn a visual model that tries to do what we want? So it's a kind of a form of a visual search. So you have a question, and you want to ask a database, and you want to get the most similar images. And in practice, what you do, make it go through a visual model, compute a visual signature. You have a visual signature database for all the images, and you try to compare all the visual signatures with each other and give you the answer. So what's clear here is like the only thing that matters is the visual model, how good it is and how well does it encode the information you care about. And of course, we use artificial neural network, and more precisely convolutional neural network, mainly because, well, they work, which is good enough reason to use them. And you can justify a bit that they work relatively the same way as the human visual cortex, but I'm sure Lev will disagree with that. Who knows?
But whatever it is, your system is a real breakthrough, so it matters. It's better than break,
so, for instance, if you look, if you take a pre-trained visual network, like a generic visual system, and you say, okay, here's my question, I have these things that I know I should find out of 50,000 images in this experiment. And if you ask just a pre-trained model, generic, like that's the ordering of where it will appear in your search. So it's the closest one will be at position 216 in your search results. So if you look in Google pages, it will be on like page 20 of the Google results. And nobody ever goes there. So that's not good enough. And it works, it shows quite well if you do like this kind of generic visual similarity. You see that naturally, it's not going to look at shape, but like more generic representation. So it, for instance, group all the drawings together, which if you're interested in the shape, in forms in a more general sense, in our case, we do, but in our case, we don't care about the medium so much. But with these visual links, you kind of have an idea how to reorganize them. So, because of the graph constraints, you know that some relationships are stronger than others. That's how you encoded them. So you can take your visual models, you take two images that you know should be closer than this one, so you know that relationship should be stronger than that relationship. So A and B should be closer than A. You take your model, and by default, that might not be the case. Like, in your space of the visual signatures, A and C might be closer than A and B. But because of deep learning, you can adapt. So you can say, well, bring that closer to that. And if you give order to convolutional networks, they are very obedient. That's yes, you can give them that. So you can modify the parameters, so that's satisfied. And the beautifulness of this model is like they generalize quite well. So, for example, if you take this other visualization, so here's like 120 images, which are either Apollo or Venus on it, or I don't remember exactly. But the way it's organized, if you do closer, they organize images naturally that have the same forms in them, either like paper drawing, engravings, or even if they're like flipped version out of this complete representation. So before we had like all the drawing in one corner, and now we have something that's much closer to what we care about, because we've inputted information in it. So if you do that, answers are much better, but still not there yet. So you put more computer vision in it, and I won't go into detail, but you try to add like spatial information and try to see what are things kind of spatially matching to improve the results. And if you do that, well, they can be like the top 5 results of your question. So you started with something that didn't even show at all in your search result to be like exactly the top 5. And these are elements, of course, that the network has never seen before. It doesn't know that this shared relationship is just because you showed it to plenty of others. Example, you can generalize to the kind of visual similarity you care about. So then you can do proper evaluation like we do as computer scientists. And here, if you want to understand a bit what that means that like 86% of the time, 82% of the time, the thing you care about will be in the top 20 results. So we're not perfect, but we're much better than 47%. So this kind of, like, you improve, of course, it's not perfect, and a system is never perfect, but you find already much more things. And that's because you input data and you input information and you have a way for the system to learn from you and you have a way to use it. And the way to use it is through, I'm totally over time, I'm sorry, is through the search engine. And I'll go quickly in that because Harold did a very nice presentation of it, so I don't really have to spend so much on it. The idea was to bring as much possibilities as possible. So you have single queries, you have multiple queries, you can search with details, you can search with metadata, you can look at this visual embedding representation. So try to bring as much flexibility as we can to the user. So it was presented a bit like this. So for instance, you start with a text query based on the metadata we extracted, of all the Madonna Bellini. There are 60-50 photographs, but only 300 independent artworks, so we already filtered this out. And then you can automatically get some form of on-the-fly computed visual embedding of what's happening there. And here, for instance, kind of a general visual landscape, continuous visual landscape, of all the Madeleine child done by Giovanni Bellini, or his workshop actually, not the workshop. And by itself, it doesn't give you an answer right away, of course. But it can also, just from an educational purpose, allow you to immerse yourself in kind of the space of the collection, the space of the visual landscape, like how are some forms of composition are reappearing, or something. And then you could do a visual search, so select one that you care about, and then you can do a visual search directly on this one. And this time without using any metadata. You can also see that this thing which is attributed to Giovanni Bellini Magnaradi, which is nobody knows where it is, are also be linked to two different attributions by Marco Bellini and Seguin. And then the results you get, you see like it's kind of patterns that were reused and like this composition was used by all the followers. Because you see like all the followers of the different the Bellini-esque school. Kind of. So I don't need that one. So just in conclusion, a couple of ideas I think important. Large data is first a necessity, because if you don't have the data as big enough, usually computational methods are not that useful. It's an opportunity, but it's also very difficult to work with, because then you need computational capabilities and you need proper engineers to do the work. What I think is the most important part is finding an operationalization of concepts to automatize is not the best word, but it's kind of this middle ground between the machine and yourself. It's kind of atomic representation of certain concepts that are precise enough, just precise enough for you to be able to use them as a researcher, but also simple enough to be fully or semi-fully operationalizable by an algorithm. And then interfaces work is really important, and I think it's really important. But at the end of the day, it's still 1% inspiration, 99% perspiration. Because it's all about execution. Because you could say, well, we put visual similarity on something, but depending on the way you do it, the quality of the results and what you can get out of it changes completely. But then at the end of the day, this case study, so this couple of this one I think was showing us really possible to index and navigate this very large collection. And I think this is kind of opening very interesting gates. Or if we take a look back, that means that we take all the photo archive, digitize everything, have the raw document accessible for everybody, keep correcting the structure, the extracted structure documents, the metadata. That's an iterative process as well. That's automatic, it's semi-automatic, but you can always correct it more and more information. Then you bring all this digital collection together, you index that, all of that, and then you can do automatically the physical links to align all the collection together, and you can do that semi-automatically as well. And then if you have enough visual links, you can create this very generic visual similarity function that keeps on improving and keeps getting better. You can have more computer scientists working, optimizing that part, and then it's all about the interface on top of that. And that's kind of the generic view of what we say. But just a couple of things that you can find with that then. For instance, that's Tiziano painting. These are, if you search with that, couple of followers, and there's the drawing by Michelangelo that was attributed 40 years before this one. And who knows if there is an actual correlation between that? Maybe there's another artwork that's not really related, or like people can come up to their ideas independently. But here it shows like it's not about directly giving you the answer, but it finds interesting elements that can bring you or help you answer some questions you can have. Another thing about the propagation of form. So here you have a bunch of Lucretia. Here's this Cleopatra. Here's Giampietro, here's Guido Reni. And you can see it's kind of almost tabular representation of, well, we can switch the kind of different elements, and it's a woman committing suicide, so you can just change what's happening there. And here's independence of form and subject. That's really clear here, you saw that. Sometimes you can even go further than that. So you're like some sleeping child. here's like sleeping Venus, and here's Madeline's child, and that would be usually interpreted as being Amore or Cupidon sleeping, and then it would be Jesus because you put a woman behind. And if you look at the visual manifold of sleeping babies, then you see a lot of porosity with the sleeping Venuses, basically. So like a whole joint interaction between them. And the final one, just for fun, so here's like the version of the rock sphere, the original one. Couple of variations, if you look at the two babies in front, they get separated independently here, independently, and then the baby itself gets separated here, and this one separated here. And then you can even get some kind of semi-variation where you modify a bit the elements that I found that was in Italy as well, where take the Virgin Mary, flip it over, and then that you keep some elements, but not all of them in a very generic sense. So, thank you for your attention.
Thank you, Benoit, for this very clear presentation, and I finally understood how it works. Thanks, I'm certainly not the only one in this room, and I finally understood in particular that this kind of system give no answers, but give us the opportunity to ask new questions. That's a very interesting conclusion. So I see Lev here in my back if you will ask me a question.
Actually, maybe fantastic, and as you said, people have been trying to build, I think, something similar for years, but yours is the first one where it works so well, right? Because at a certain point I gave up on the specific visualizations because I thought it doesn't work very well, but apparently it can work. So maybe it's like no day, but I actually have a simple technical question because I didn't understand some basic things. So what kind of learning? Is it convolutional network? Or different kind of, what kind
Yeah,
of,
it's convolutional network.
so in this case, right, if you train convolutional network, you need to have some training data. So what's the training data in this case?
Well, that's the graph I was showing. Because when you train
Yeah,
convolutional
but how do you
network,
get the graph? How do you get, I mean,
the graph it's through user interaction. It's basically me and colleagues kind of going in the data and say like, oh,
okay,
okay.
so you basically create graph data.
Yeah, we modeled, yeah.
Okay, because that was not.
Yeah, maybe. Sorry
But
about
it's
that.
important, right?
Yeah, it's really important.
Is it, because like how do you train this, right?
Yeah. But the thing here that was important is you can start with a base system that's in train, and also with if your interface and your search interface is good enough, you can already find things because you're already examples, or you can search with master and followers because there will be visual correlation there. So you can use expert knowledge to kind of bootstrap the system and make it get better and better. And the better it gets, the more you find.
Just a very quick last year. So we understand, right? You go through a system, you say this is similar to this is, and when you say this is similar to this, you actually don't specify how similar. You simply say these two things are related. So you create lots of this kind of binary. I mean, not binary. What's the problem?
So binary connections.
Yeah, you create a connection, and when the system extracts features and says this is how I have to present the data to match with graphs.
Yeah, kind of create some form of neighbors. And say, these have to be neighbors somehow.
Right, and I think visually it seems to me the results you're getting a much higher quality when people are able to get with typical kind of dimension reduction, even t-SNE. It seems like you approach this.
Yeah, it's because of the changing of the, depending on the, it's all about the quality of the visual model.
It's also because it's like one period maybe, yeah.
I think it works mainly here. We're focusing on Italian art of the Renaissance. It's still very specific. It will still work if you apply it. We've applied it sometimes for other projects for illustration and history of the books as well. But it wasn't, of course, it's not as compelling as the data you actually trained.
And the system is currently online, right?
That so the version Harold was showing on the Time Machine website is not as complete as the version I did for my PhD I was working with. Okay. But there's a public version that implements most of the feature on the Diamond Time Machine.
Okay. I will start promoting for my channel. Okay.
Questions?
Do you have an idea of the structure of your graph?
Yes.
what's its maximal degree, what's the diameter, what's the number of edges as compared to the number of nodes.
So if you actually look at the graph, they are usually more very neighboring structures. So it's not highly connected at all. Because if you wanted to be highly connected, it's almost impossible as a human to edit it properly. So it's more like, oh, locally I will look at this very specific kind of standard representation. I will like work on that things, or like these are all very close variation to each other. So, for instance, the situation where there's like very complex graph as a baby's propagation, and I think that's not super relevant, super representative of the type of graph. The graph is quite simple actually. Like
but completely connected, however, or
no,
not?
No.
There can be many connected components.
Yeah. Like usually there are small islands that are easy to reason with. Like there's a lot of there's not so much there's not so. I mean, I mainly did the annotation by myself when I was playing with it. So a lot of things which are not annotated, but because the system is so good at generalizing, that doesn't matter.
Couldn't you explore inattended connection when if you forced your graph to be connected? Maybe some relation you didn't thought about could appear if you.
Well, the relation appears already when I was showing, because sorry. So for instance, when I was showing this one. Yeah, this one. So when I was showing here the manifold of the Bellini like the manifolds of Giovanni Bellini, here you might see a few blue lines of things which are connected with each other. These are the only the blue lines are only annotated things. So there are a few that I found kind of randomly going around. So it's like a kind of small blue line that there are. But you see very few things are actually annotated. It's just like, oh, by the way, these things should be close to each other. You should know that. But all the rest of the organization of the space is done automatically. So, and that's very important actually, because doing this kind of representation, we've actually done other user studies that we ask students to try to annotate more connections, to try to increase the graph. And if you use this kind of visualization, it really helps. And it really helps also depending on the quality of the visual model you already have. Because if your visual model is already good, then it will naturally group things probably close to each other. So it pre-selects the connection for you. So by just looking at the manifold, you say, oh, well, these two are really not so far from each other. They might be not close enough. But this is the visual similarity kind of prepares the space for you. It really helps navigating. It doesn't give this kind of landscape. The plot has no meaning by itself. It's just like helper for exploring. No more than that.
Little question. If you could have power more puissance de calcul plus grande, le système est-ce qu'il serait meilleur?
Oui, mais pas extrêmement. I'll just answer in English.
English,
yes. No, it will improve, of course. Like the more computational, better. The more computational, the better. Especially because here we have an interactive system. So when you ask a question, you have kind of a budget of computation. I need the answer to go back to the user in 5 seconds. But there are some situations where, as a researcher, like I'm willing to pay the computational cost. I can wait a week if I'm sure the result will, if just there's a tiny percentage, like the result will be a tiny bit better, because I don't care. I can wait. But we're in the age of Google, when everything is accessible in 2 seconds. We grew up we've been spoiled a bit. So when you create this kind of system, there's always like a time limit constraint. Like, if we do something that's too slow, nobody will ever use it, and nobody will care. Yes, please.
In the last slide, you showed that scheme where we saw the user on the very right and the different possibilities how the user can interact with the system. I'm very interested in that. A general question to the whole audience is user-generated data a challenge or an opportunity? I asked for a simple reason because our Artigo system, where we created user-generated data via gamification, we get millions of tags to thousands of objects, and the criticism usually is that there are a lot of mistakes, that people tag it incorrectly. For example, there is a gesture like the hand in the code, and everyone tags it Napoleon, even if it's not Napoleon, because at that time a lot of people were depicted like this. So this is called incorrect. But I usually explain that there is no right or wrong, and I explain what our data, our tags represent. They don't represent a truth, only a truth about the contemporary, about viewers today. How people today see the historic artworks. And then it would be interesting if we keep that data and in 50 years we still have that project running and we could see how seeing what people over time see in those objects. And what I think happens here is what you said, this manual training of the network also trains the network with contemporary viewers and not the viewers of the time of creation, which is of course natural. And the question is that good or bad? Is that something we must be aware of, or is just a natural part of it?
Well, you always have to be aware of it, like what do you train on and what does it bring. Like there's